Welcome back to Mathematics Lifeline. This is episode 2 of our integration practice series where I give you two integrals, let you try them out on your own, and then I will go through them step by step. So if you haven't seen the first episode, I recommend you go watch that. But essentially, this series is for Calculus 2 students who are just learning strategies for integration. I know these can be tricky, so it's good to have the extra practice. So the first integral is a definite integral, so we're looking for a number here, and it's from 0 to 1 of x cubed e to the x squared dx. And the second integral is indefinite, and it's the integral of x cubed over the square root of 4x squared plus 16. So I'm going to go ahead and let you try these out, and whenever you get an answer, unpause the video, and I will start working these solutions on the board. All right, so hopefully you made some progress on these integrals. This is the first one that I'm going to work through on the board. The definite integral from 0 to 1 of x cubed e to the x squared. Now, the nice thing about this one is that there are two valid starting points. You can either start with a substitution, or you can start with integration by parts. But either way you start, you'll have to do the other one. So we need both a substitution and an integration by parts in this. I think the easiest way to go about it is going to be to start with a substitution. So because I know we're going to be doing a substitution and integration by parts, I'm going to use U for the integration by parts. So I'm going to do a W substitution here. The same process, I'm just using a different letter. So I'm going to say, let's let W equal x squared. Now this may look like a weird substitution at first because you usually will start with the higher degree term and hope it comes down. But because this x squared is in the exponent of the e, right, we're not going to be able to use dw to get this out of the way. So we're going to have to start with that x squared, which means that dw is going to be 2x dx. And before we go on, I'm going to say that dw over 2 is equal to x dx. So what we've done here is we've said, okay, now this exponent for this e is going to turn into a w, and we're going to change this integral in terms of dw, right? So we're going to get rid of an x dx, and we need to pull the 1/2 out front from this dw over 2. So we're going to have 1/2 times the integral, and we want to figure out what's left on the inside. Well, we know that what we've started with was this substitution that we have e to the w. And we know we're going to need dw. But now the problem is we only got rid of 1x whenever we did the substitution. So we still have an x squared out here. But that's good because in our substitution we said w was equal to x squared. So all that does is that x squared that's left over just becomes another w out front. So now we have the integral, 1/2 times the integral of w e to the w dw. And I'm going to drop the bounds for this one just because I think the bounds will get a little in the way. We'll bring them back in at the end. But now you see that we've done this substitution. This integral right here is a very, very standard integration by parts. This may have even been the first one that you did in your calculus class. So we're going to choose u to be the function that gets easier to work with as we differentiate it. So that's just going to be the w, which means that du is going to be dw, of course. And then our dv is going to be the one that's easy to integrate, or the other one that we didn't choose. And that's going to be the e to the w. So dv is going to be equal to e to the w, dw. And when we integrate that to get v, of course, it's just going to stay as e to the w. So now we want to use our integration by parts formula. So we have that's uv minus the integral of v du. So don't forget the 1/2 out here, but we have the 1/2, and then we're going to do the integration by parts formula. So uv is going to be w e to the w minus the integral of v du. So that's going to be e to the w dw. And now you see we've brought this integration down to just e to the w, which is very, very easy to work with. So this is really the same as 1/2 multiplied by w e to the w minus, well, the integral of e to the w is just going to be e to the w. And of course, this is going to be evaluated over the bounds, but we need to switch back into x first. So I'm going to leave this out for right now. I guess one more thing we can do is to make it a little bit simpler. We'll just multiply this 1/2 into everything. So we're going to have 1/2 w e to the w minus 1/2 e to the w. Okay, so now we've got the integral in the w world done, but we need to change this back into x. So remember w is x squared, so we're just going to replace that. So what we have is 1/2 x squared e to the x squared from this w e to the w minus 1/2 e to the x squared. And now we'll reintroduce the bounds because the bounds were from 0 to 1 in the x world. So that's what we have. So now all we need to do from here is just go ahead and plug in. So we're going to plug in 1. So we're going to have 1/2 times 1 squared e to the 1 squared minus 1/2 e to the 1 squared. That's plugging in 1. And then when we subtract off plugging in 0, well, we see the first thing that we do when we plug in 0 is get this whole term right here just goes to 0 because we're multiplying by 0 here. So we're going to get 0 minus 1/2 e to the 0 squared. So now we're going to go ahead and evaluate everything in here. Well, here we have 1/2 times 1 squared, so it's going to be 1/2, and then times e to the 1, so it's just going to be e over 2 for this first part. And we're subtracting off 1/2 e to the first power, so of course that's going to be another e over 2. And then here we're subtracting off 0 minus 1/2 e to the 0. Well, e to the 0 is 1, so we're just doing 0 minus 1/2. Now, of course, e to the over 2 minus e over 2, this goes to 0. So we're just subtracting a negative 1/2, so it's going to give us a positive 1/2, and this will be our numerical solution for this integral. So really, it's not that hard if you pick the right substitution and do the right process, but knowing that you need to do a u sub into integration by parts could be a little tricky for some people. But yeah, that's it for the first question. Hopefully you did well on this one, and we'll go ahead and start the second question right now. All right, so here is integral number 2. So hopefully you were able to get somewhere with this one. This one is a little tricky as well. So we're going to go ahead and get started right now. So what we're going to do is we're ultimately going to be doing a trig substitution here. And you may have kind of got that picture from this denominator, but we need to kind of manipulate it just a little bit before we can do that. So what we're going to do is we're actually going to factor a 4 out of this denominator. So we're going to have, this is the same thing as the integral of x cubed over the square root of 4 times the square root of x squared plus 4 dx. Now remember the square root of 4 is just going to be 2, so we can pull a 1/2 out of this integral, and we'll just have 1/2 times the integral of x cubed over the square root of x squared plus 4. So now at this point we're looking more like a normal trig substitution, because in the denominator we have the square root, I'm going to write it over here, we have the square root of x squared plus a squared. And what that tells us to do is going to be to let x equal a tangent theta. That's going to be our substitution. We need to choose a tangent theta. Well, in this case, a is going to be equal to 2 because 4 is 2 squared, and that's what we have right here. So in our case, we're going to say let x equal 2 tangent theta. And if we let x equal 2 tangent theta, then we know that dx is going to be equal to 2 secant squared theta, d theta. So now that we have this, we can go ahead and move right into our trig sub, because we have this integral right here. Now everything is going to be in terms of theta. So we have 1/2 times the integral. Well, x cubed is going to be 2 tangent theta cubed, which is going to be 8 tangent cubed theta, over, we have x squared plus 4. Well, that's going to be the square root of 4 tangent squared theta plus 4. And we're getting this just from squaring x, right? And that's going to be 4 tangent squared theta. And then don't forget that dx is now changed into 2 secant squared theta. So times 2 secant squared theta d theta. Okay, so now, again, we're going to factor a 4 out of this square root down here. And when we do that, we're going to, I'll just rewrite it. We'll have 1/2 times the integral of 8 tangent cubed theta over, well, this is now going to be, when we factor out a 4, it's still under the square root. So we need to take the square root of 4. So we're really taking a 2 out of the square root. And then we have the square root of tangent squared theta plus 1. And again, this is still times 2 secant squared theta d theta. Okay, so now we've got this into a form where we can simplify and bring out all of the constants. So of course, these 2's are going to cancel right here. And then we have this 8 we can pull out. So we're really going to have 4 times the integral. The tangent cubed is going to stay on top. So tangent cubed theta. We'll pull the secant theta over, or secant squared theta right here. And then we're dividing by, well, what is this square root going to turn out to be? Well, there is a Pythagorean identity that can help us here. We know that tangent squared plus 1 is always equal to secant squared theta. So that means that if we have the square root of secant squared, so it's just going to be a secant theta on the bottom. And then we can cancel a secant theta. So we're going to have 4 times the integral of tangent cubed theta secant theta d theta. And that is what our trig subintegral has turned out to be. So it's a little ugly looking still, and we still kind of need to work with it a little bit, but it shouldn't be too bad. And the reason is because we're going to use this same identity here to help us out with this tangent cubed. So what we're going to do is we're going to break this up, the tangent cubed, into tangent times tangent squared. So if we knew that tangent squared plus 1 was secant squared, then we could say that tangent squared is equal to secant squared minus 1. So we can really rewrite this integral as 4 times the integral tangent theta times secant squared theta minus 1 times secant theta d theta. So it's a little bit ugly, but the nice thing about what we have here is that if we choose u to be equal secant theta, so we're going to say u equals secant theta, well then we have du to be secant theta tangent theta d theta. And if you notice, we can say this is now going to be u squared minus 1, and the secant theta tangent theta d theta all goes away with this u sub. So this is really 4 times the integral of u squared minus 1. And again, this is du. So we were able to break that tangent up, and then now we can get this into a u sub, and now this is a much easier integral. So of course, this is going to give us 4 times u cubed over 3 minus u. And remember that u was equal to secant theta. So we have 4 thirds secant cubed theta minus 4 secant theta. So we have this in terms of theta now, and we want to get it back in terms of x to find our antiderivative. So how can we figure out what secant theta is? Because we don't really have that yet. Well, this is where we're going to need our triangle. That's always really helpful with trig subs. So we're going to set up a triangle down here, and we're going to try to make it match our situation that we have. So we're going to choose this angle to be theta. We're going to choose this side to be x. And we said that x was equal to 2 tangent theta. So that means tangent theta should be x over 2. So that means this side length should be 2, which now using the Pythagorean theorem, we can say that this is the square root of x squared plus 4. So given that, we can find that secant theta is going to be equal to the hypotenuse over the adjacent. So secant theta is the square root of x squared plus 4 over 2. So we know that now. We can go ahead and rewrite all of those secant thetas in terms of x. So we're going to have 4 thirds times secant theta cubed, right, which is going to be the square root of x squared plus 4 over 2 cubed, minus 4 times secant theta, which was the square root of x squared plus 4 over 2. And now we're just going to go ahead and simplify this out. So now that we have it in terms of x, we can add the plus c at the end. And then we're going to simplify as much as we can. So when we cube this one, we're going to have a 1/8 as a fraction out here. So we can kind of multiply this over here, and we'll get a 1/6. So this becomes a 1/6 multiplied by this cubed, right? Well, that's going to be x squared plus 4 times the square root of x squared plus 4. Is what that turns into. And then over here, we just have minus 2 because the 4 and the 2 will divide. So 2 square root of x squared plus 4 plus c. Now, there's one more thing we can do here. Since these are both being multiplied by x squared plus 4, we're actually able to combine these into one product here. So we have a 1/6 out here. So that means that this is going to be 12/6. So all we're doing is going to be subtracting 12 from this and then combining them into one fraction. So this is going to be equal to 1/6 times x squared minus 8 square root of x squared plus 4 and the plus c. Now, that is an ugly answer, but it actually is the correct answer for this case. Now, I kind of want to explain what I did right here again because this might have confused you a little bit. So essentially, we're trying to put these into one fraction, basically, because this is all over 6 in essence. So we need this denominator to be 6. So we're really subtracting 12, right? We're subtracting 12 root x squared plus 4. So when we do that, we can just kind of work with these constants. So we're taking 4 minus the 12. So the x squared plus 4 will now become an x squared minus 8, and everything else will stay the same. So you can kind of work with that simplification if it's a little fuzzy, but this is the correct answer, and that is the end of integral number 2. So again, kind of a long one, kind of tricky, because even halfway through this integral, we still have to figure out how to integrate this one, and that can still be tough for some folks as well. But yeah, hopefully this was helpful. Hopefully you got these correct. If not, and you need some more clarification, feel free to ask in the comments. I'd be glad to answer any questions that you have. But yeah, I hope you enjoyed this video, and I will see you in the next episode. Thanks for watching.